In this lesson, we're going to learn about the factored form of a quadratic function and how to use that form in order to find the zeros. There are several different forms that a quadratic function can take on. Standard form, which you see here, vertex form, which you see here, and factored form, which we see here. Each of these forms, although they look incredibly different, are equivalent functions. If we were to look at the graph of each, the graphs are identical. And if we were to look at the input and output tables, the input and output tables are the same from function to function. So why would we want to have three different forms of the same function? The truth of the matter is that each form tells us something a little bit different. The standard form, for example, tells us the y-intercept. In this case, we can see from the -8 at the end that the y-intercept is at the point 0, -8. The vertex form tells us about the shift of the function from the origin. This function shifts right 1 and down 9, which tells us that the vertex is at the point 1, -9. The factored form tells us about the zeros. If we take each of the factors and set them equal to 0, we can learn the location of the zeros of the function, and that's what we're going to learn about today. Let's begin by taking a look at some examples. Write the function in factored form, then find the coordinates of the zeros. The first function is y equals x squared plus 5x plus 6. Remember, we have various ways to factor. We always start by looking for a greatest common factor. We look to see if we have a difference of two perfect squares, and then we have a way where we can factor quadratic trinomials. If you need help with factoring, go back and see the videos on factoring. Here we have a quadratic trinomial. We need numbers that multiply to 6 and add to 5. We could make a list of the possible candidates, 1 times 6, 2 times 3, and their negative counterparts. The pair that adds to positive 5 is 2 and 3. Because we have a leading coefficient of 1, it would be very simple to factor this right away to x plus 2 times x plus 3. Or, if you prefer, you could use the grid. If you use the grid, remember we put the x squared in the top left box, the plus 6 in the bottom right box, and then our two numbers with the variable attached in the other boxes. Now we look across the top for the greatest common factor, x, and we use multiplication to fill in the other spots around the grid. X times something is x squared, x times x. X times something is 2x, x times 2. And now multiplying down, x times something is 3x, x times 3. And we can check 3 times 2 gives me 6. So my factors are x plus 2 times x plus 3. We can now take those factors to write our factored form. Because the original function was y equals, we'll write this as y equals, and then our two factors x plus 2 times x plus 3. That is the function in factored form. Now let's use that form to find the zeros. Here's how we do it. We take each of those factors, x plus 2 and x plus 3, and write each one equal to 0. X plus 2 equals 0, and x plus 3 equals 0. Now we solve each of those little equations. On the first one, we subtract 2, and we have x equals -2. On the second one, we subtract 3, and we have x equals -3. This tells me the x value where those zeros are located. X equals -2 means I have a 0 at the point -2, 0. X equals -3 means I have a 0 at the point -3, 0. Those are the zeros of the function. We can always verify this by looking at a graph. Notice the graph of the functions shown right here. The zeros, where the graph passes through the x-axis, sure enough, are at -2, 0 and -3, 0. Here's a second function, f of x equals x squared plus x minus 20. This one's for you to try. See if you can write the function in factored form, and then identify the coordinates of the zeros. Please pause the video here, and come back when you're ready to compare answers. Let's compare our answers. We begin by factoring the quadratic trinomial. We need numbers that multiply to -20 and add to positive 1. We list out the possible candidates for those numbers, and we identify the pair that adds to positive 1, negative 4, and 5. We can factor this right away because our leading coefficient is 1 to x minus 4 times x plus 5, or we could use the grid. And we'd fill in the grid as we normally do, find the greatest common factor across the top, and then use multiplication to fill in the other spots around the grid. This time, our function was called f of x, so the factored form will also be called f of x. The factors are x minus 4 and x plus 5. That is the factored form of the equation. Next, we want to find the zeros. We find the zeros by taking each of the factors and setting them equal to 0. Solve each one for x, and that will give you the location where the 0 is located. We have a 0 at x equals 4, so the 0 is 4, 0. We have a 0 at x equals negative 5, so the 0 is at negative 5, 0. Remember, we can always verify these on a graph. If we look at a graph of the function, notice sure enough we have a 0 at negative 5, 0, and a 0 at 4, 0. Sometimes the zeros are not at integer values. Take a look at exercise 3. F of x equals 5x squared plus 17x plus 6. There's no greatest common factor. This is not a difference of perfect squares, but it is a quadratic trinomial. We need numbers that multiply to 30 and add to 17. So I list out the candidates, the numbers that could multiply to 30, and I'm going to choose the one that adds to 17. Those numbers are 2 and 15. I'll use my grid this time to do my factoring, and I'll fill it out with the 5x squared in the top left, the 6 in the bottom right, and the 2x and 15x in the other two boxes. I do my factoring across the top, taking out first the greatest common factor, and then I use multiplication to fill in the other spots around the grid. The factors are 5x plus 2 and x plus 3. The function was f of x, so the factored form will be written with f of x. The factors 5x plus 2 and x plus 3 give me my factored form of the function. Now I want to find the zeros. I take each factor, 5x plus 2, and make that equal to 0, x plus 3, and make that equal to 0. Solve each equation for x. Subtract 2, divide by 5, x equals negative 2/5. In the second equation, subtract 3, x equals negative 3. These tell me the locations of the zeros. X equals negative 2/5 means I have a 0 at negative 2/5, 0. X equals negative 3 means I have a 0 at negative 3, 0. Once again, we can confirm this by looking at the graph of the function. Notice I do have a 0 at negative 3, 0. It's very clear to see. And then I have one that's between 0 and negative 1 on the x-axis, and it looks about at negative 2/5. It would be very difficult to tell that was negative 2/5 from the graph, and therefore we now see the advantage of factoring. Factoring lets us see the zeros even when they're not easy to read from a graph. Exercise 4 is for you to try. Can you write this function in factored form and then find the coordinates of the zeros? Please pause the video here and come back when you're ready to compare answers. Let's compare answers. We're looking for numbers that multiply to 18 and add to negative 11. We list out the numbers that are possible candidates, and we find the pair negative 2 and negative 9 both multiply to 18 and add to negative 11. We then use the grid to do our factoring. We find that the factors are 3x minus 2 and x minus 3. Since the original function was written as y equals, the factored form will be written as y equals. The factored form is y equals 3x minus 2 times x minus 3. Now we want to find the zeros. We take each of those factors and set them equal to 0. When we solve the first one, we have x equals 2/3. When we solve the second equation, we have x equals 3. That means we have a 0 at 2/3 0 and 3 0. As always, we can compare these on a graph and see if they match. Notice we do have a 0 at 3 0, and it looks like we have one somewhere between 0 and 1 on the x-axis. It looks about like 2/3, though it's hard to read. And again, that's the advantage of factoring. It allows us to find the zeros that are difficult to see on the graph. In exercise 5, we have a quadratic trinomial. This time we have a greatest common factor. Notice we have a common factor of 2. So the first step this time will be to factor out that greatest common factor. Now we're left with a trinomial, x squared plus 6x plus 5. That trinomial can be factored. We need numbers that multiply to 5 and add to 6. We look at the possible candidates, and the numbers that meet this criteria are 1 and 5. 1 times 5 is 5. 1 plus 5 is 6. Now I can either take those and go right to my factored form, because I have a leading coefficient of 1 in the parenthesis, or I can go ahead and use the grid. Either method is acceptable. If I use the grid, I find the greatest common factor across the top, which is x, and then use multiplication to fill in the spaces around the grid. My factors are x plus 1 and x plus 5. And so the factored form of the function is y equals 2 times x plus 1 times x plus 5. Now let's find the zeros. When I find the zeros, this time I have 3 factors to consider. My first factor is 2, so I write 2 equals 0. My second factor is x plus 1, so I write x plus 1 equals 0. My third factor is x plus 5, so I write x plus 5 equals 0. Let's go through them one at a time. 2 equals 0. That makes no sense, so there is nothing here to work with. We move on. The second factor, x plus 1, we subtract 1 from each side, and we have x equals -1. We now know the location of our first 0. X plus 5, we subtract 5 from each side of the equation, and we have x equals -5. That's the location of my second 0. So I have zeros at -1 0 and -5 0. As always, I can compare this with a graph of the function. If I look at the graph, notice sure enough I have zeros at -1 0 and -5 0. Exercise 6 is for you to try. Begin by taking out the greatest common factor, and then factor the resulting trinomial. Write the function in factored form, and then find the coordinates of the zeros. Please pause the video here and come back when you're ready to compare answers. Let's compare answers. The greatest common factor here is 3, so we begin by factoring a 3 out of the trinomial. That leaves us with x squared minus 5x minus 14. Now we have to factor the trinomial. We need numbers that multiply to -14 and that add to -5. We look at the possible candidates, and we find that 2 and -7 are the pair that we're looking for. Those two numbers multiply to -14 and add to -5. I can then set up the grid to do my factoring. And when I do, I find the factors are x plus 2 times x minus 7. The original function was f of x, so the factored form will be f of x. Don't forget the common factor of 3, and then the two binomials, x plus 2 times x minus 7. That is the function in factored form. Now we want to find the zeros. Once again, we take each of the 3 factors and set them equal to 0. The first one says 3 equals 0. That makes no sense, so there's no 0 to find there. The next one says x plus 2 equals 0, and we solve to find that x equals negative 2. The last one says x minus 7 equals 0. We solve to find that x equals 7. So therefore we have two zeros in this function, one of them at negative 2, 0, and one of them at 7, 0. As always, we can compare this with a graph. If we look at the graph of the function, we notice that sure enough we have a 0 at negative 2, 0 and a 0 at 7, 0. In the next exercise, we're going to look at a quadratic function that looks a little bit different than those that we've seen already. This one is a difference of two perfect squares, and we know we can factor a difference of two perfect squares into a conjugate pair. X times x gives me x squared, and 6 times 6 gives me 36. Plus the two terms are connected by subtraction. We can factor this to f of x equals x plus 6 times x minus 6. Now that we have the factored form of our function, we're ready to find the zeros. As always, we take our two factors and set them equal to 0. X plus 6 equals 0, and x minus 6 equals 0. Now we solve each one for x. X equals negative 6 is what we have in the first factor, and x equals 6 is what we have in the second factor. This gives us our two zeros. X equals negative 6 means I have a 0 at negative 6, 0. X equals positive 6 means I have a 0 at positive 6, 0. As always, if we compare this with the graph of the function, we notice that sure enough the zeros are at those 2 points, negative 6, 0 and positive 6, 0. The last exercise for today is for you to try. Can you factor this difference of perfect squares, write the function in factored form, and then find the coordinates of the zeros? Please pause the video here and come back when you're ready to compare answers. Let's compare answers. We notice that this is a difference of two perfect squares. X times x gives me x squared, and 9 times 9 gives me 81. The two terms are connected by subtraction, so I can factor these into the conjugate pair x plus 9 times x minus 9. Because the original function was y equals, we will write our factored form with y equals. Now we're ready to find the zeros. We take our two factors, x plus 9 and x minus 9, and set them equal to 0. Solve each of the equations to find that x equals negative 9 and x equals positive 9. This means that we have zeros at negative 9, 0 and positive 9, 0. And as always, if we compare with the graph of the function, we can see sure enough that that's where the zeros are located. So now you know how to use the factored form of a quadratic function in order to find the zeros. It's a very powerful skill, and it's worth learning and feeling comfortable with. Remember, you can learn more about factoring quadratic functions in Mr. Dorey's Algebra Handbook, available at www.doreypublications.com.